Look at this particle beam. To understand the physics governing this energy, you have to accept one absolute rule. The speed of light in a vacuum is exactly 299,792,458 meters per second, no matter how fast you are moving. By the late 19th century, optical experiments like those conducted by Albert Michelson proved that classical mechanics couldn't handle this speed limit. Velocities simply didn't add up the way standard physics predicted. To keep the speed of light constant, physicists needed a completely new architecture for space and time. This arrived through the mathematics of H.A. Lorentz. Albert Einstein took that mathematical framework and used it to rebuild the physics of measurement itself. One of the most famous consequences of this math is Lorentz contraction. If you hold a ruler in your hands, you can measure its length easily. Because it is at rest relative to you, physics calls this the proper length. But if someone else measures that exact same ruler as it flies past them at high speed, the results change. As this rod moves along an axis at 90% the speed of light, the transformation equation shows us that the measured length is physically shorter. It is reduced by the Lorentz factor, gamma. Apply this to a three-dimensional object moving at that same relativistic speed, and the geometry squashes flat in the direction of motion. Because of this, it is commonly taught that if you were to take a photograph of this cube as it flew past, the image on the film would show this exact flattened shape. This is wrong. In relativistic physics, there is a strict difference between the mathematical operation of observing an event and the optical phenomenon of actually seeing it. The Lorentz transformation only calculates the coordinates of an observation. It assumes a theoretical grid where information is gathered instantly, completely ignoring how long it takes light to travel to your eye. Seeing, or photographing, requires photons to physically travel through space and arrive at a single, localized point, like a lens, at a specific moment. When objects move at everyday speeds, the time it takes light to bounce off them and reach a camera is so small it doesn't matter. In this case, observing and seeing are functionally identical. But as objects accelerate toward the speed of light, those photon arrival delays stretch out. The light itself distorts the optical image, tearing it away from the coordinate reality. A photograph of a relativistic object captures an image that fails to show the physical contraction we expect. To find out what the camera actually sees, we have to account for the object's depth. Relativity defines an observation apparatus as a vast three-dimensional grid floating in space. At every interception sits an observer with a clock. When a moving rod passes through, two observers record the exact coordinates of its ends at the precise same instant. This simultaneous multi-point coordinate snapshot is what mathematically proves the contracted length. Now abandon the grid. Watch what happens when we rely on the optical reality of a camera lens. A camera sits at a single origin point. A photograph is taken when the shutter opens for 1 instant. You can map the light entering this lens as a collapsing spherical shell of photons, shrinking rapidly until it converges onto the sensor. Any photon recorded by that camera at time 0 had to be traveling on the surface of that specific collapsing sphere. Because objects have depth, the photons arriving at the lens simultaneously must have been emitted by different parts of the object at entirely different times. In the Weisskopf cube thought experiment, a camera photographs a moving cube of length L perfectly perpendicularly. Light from the rear edge must travel an extra distance of L to catch up. To hit the camera lens simultaneously, the rear photon must be emitted earlier. Specifically, it was emitted earlier by a time interval of L divided by the speed of light. But this object is moving. During that earlier time, the entire cube was physically further back along its flight path. The cube was physically further back by a distance equal to its velocity multiplied by that time delay. Because the rear photon was emitted then, the camera captures light from the side of the cube, a surface that should be completely invisible perpendicularly. Let's look at this split screen showing what arrives on the camera sensor, starting on the left. The front face of the cube arrives, physically Lorentz contracted to a width of L times the square root of 1 minus v squared over c squared. Next to it, the camera records the side face, its width determined by the optical delayed distance, L times v over c. Combine these for the final optical projection. On the right, a stationary cube rotates. Its geometric silhouette perfectly matches this relativistic projection. Today, physicists call this the Terrell-Weisskopf effect. Lorentz contraction is a physical reality, but optical delay perfectly masks it. At extreme speeds, the flattening is converted entirely into apparent rotation. This is why advanced physics demands strict operational definitions. Failing to separate the coordinate grid from an optical sensor leads to a flawed understanding. The breakdown of absolute simultaneity forces a reconstruction of the causal geometry of light reaching our eyes. Relativity binds the coordinates of space and the optics of sight into a single warped reality.